Hello, welcome to my project. My name is Patrick Fitzgerald. This was a project that I worked on for ADS 635Z1 Data Mining 1 for Baypath University. This is the final project for this course. My topic was Machine Learning March Madness, which is a Google Cloud competition on Kaggle in which you try to minimize the log loss for NCAA tournament predictions. Right here. Just to start with an overview, the NCAA Division I basketball tournament is one of the most exciting sporting events of the year, thanks to upsets, Cinderella stories, and unpredictability that comes with it. Millions of fans, basketball and non-basketball fans, fill out their brackets every March to participate with hopes of achieving an improbable perfect bracket. Just how improbable? Given you know a little about basketball, your odds are conservatively at 1 in 128 billion. The goal of this contest was to utilize past tournament results to build and test models in order to forecast outcomes of all possible matchups in the 2019 NCAA Division I basketball championships. So for my purposes, I did both men's and women's. For the men's, I stuck to the parameters set by the actual competition, trying to minimize log loss, and then I used my model to actually create a bracket for the women's. I did not create a bracket for the men's, just to get that out of the way at the beginning here. These outcomes are to be computed probabilistically. Each final submission is evaluated and ranked on the public leaderboard. This would be if I were actually participating in the Kaggle challenge, but I didn't because the competition is over. I did look at my log loss scores and compare them to those of people who did compete and or did all right. I didn't do great, but it was my first attempt, so not too bad. They're based on log loss. So if you aren't familiar with log loss, the important thing is that smaller log loss is better. The use of the logarithm provides extreme punishments for being both confident and wrong, as seen in the formula here. Log loss. We want to minimize this function, where n is the number of games played, y hat I is the predicted probability of team 1 beating team 2, yi is 1 if team 1 wins, 0 if team 2 wins, and log is just the natural base E logarithm. EDA. I did this in both Python and R. Python for just the straightforward EDA, and then I computed some advanced statistics in R. So as anyone who is even relatively aware of March Madness can tell you, a team on a hot streak heading into the tournament is likely to continue winning if not heavily favored. A great example of this would be Kemba Walker's UConn Huskies team from 2011 that won, I want to say it was the NIT tournament, don't quote me on that, but they won a bunch of games in a row leading up to the tournament and then were on such a hot streak that they eventually captured the title. This is sort of an important place to start as it assisted in focusing my attention when it came time to feature selection and feature engineering. Anyone who knows about basketball over the last 7 years or so, advanced analytics has become all the rage. A great example would be the NBA's Houston Rockets. They tried to basically math their way to a championship and came one quad injury away, basically. With that in mind, I tried to look a little deeper into some of the more advanced metrics to see if they might give me an edge when it came time to actually build my model. So, you start by looking at teams that consistently rank amongst the best year in and year out. Some familiar teams appear at the top seeds consistently. This is for the women's here. This is what we're looking at, just speaking generally about the women's tournament. UConn holds the record for most consecutive wins, 111, including 2 consecutive national championships. Unsurprisingly, their average seed is less than 2. They're almost always a 1 seed. Interesting, this year they were actually a 2 seed. Duke basketball is a powerhouse for both men's and women's. Women's Tennessee team has made every tournament since the NCAA began sanctioning women's sports in the 81-82 season. They were coached for 38 years by Pat Summitt, who retired as the winningest coach in college basketball history, including 8 national championships. Another thing to look at is since Coach Mulkey took over the women's Baylor team in 2000, they've made the tournament 19 consecutive times, won 3 national titles. So since they didn't go to the tournament as many times as some of these other teams, the fact that they were number 1 seeds 10 times drives their average quite low. So if you look at just the average seeding here, You can see these are the teams, the top 15 teams, and their average seeding. So it looks like UConn, Duke, Tennessee, Baylor, South Carolina, and these are the kind of teams that you're going to see go far in their tournament year in and year out. You're always going to see them do well, and that's the case this year as well. National championship game results. The data set provided for the women's tournament goes back to 1998, 1985 for the men, 98 for the women. So this is for the women, it goes back to 1998. You see a lot of familiar teams on these two lists, so basically the top teams are consistently either making it to the championship game and winning, or making it to the championship game in general. The higher ranked teams end up making it farther in the tournament than lower ranked teams, and this is going to be reflected in my model. There are some teams in here that did not crack the top 15. This could be due to taking only 15 teams, and maybe if I had taken more, these names would have shown up. But also it might have something to do with some Cinderella teams, which is something that, again, is going to come up later in my model, and I'll discuss that. Seeds from the tournament and regular season winners and losers. This is a plot of the winners of the tournament, their seed, and the count number of times they won. This is the regular season, the winning seed, and the number of times they won. Tournament, losing seed, number of times they lost. Losing seed, number of times they lost. Regular season. So you can see that in the tournament, the top seeded teams are heavily favored. Very rarely do you see a low seeded team win. Very rarely do you see a high seeded team lose. You can see over here that these are all pretty consistently up here, whereas you don't see a 1 or a 2 seed get taken down very often. And that's reflected in the regular season data as well. We have sort of this trend that's kind of we're following. It mostly goes up here. Your low seeded teams are typically teams that do well in the regular season. That's how they get their ranking in the tournament, although there is this little dip here, which means that there is decent parity throughout the nation. On any given day, any team can win, and that's kind of what you expect. Basketball is, however, a little more consistent than some other sports. Typically, the better team will win. Look at as well is the winning location, namely home court advantage, because this is going to come up when I do one of my later models, the ELO model. Home court advantage is going to be pretty important. And you can see that the home team is typically the victor. That's pretty much the case throughout any sport, really. The home team advantage is something real and quantifiable. Typically for basketball, it's about 3.5 to 5 point margin of victory. That's typically, home court advantage will give you about 3 extra points or so, generally speaking. Not many regular season games are played in neutral locations. However, the tournaments are almost exclusively played in neutral locations. It's very rare that you have someone playing a home game in the tournament. So although this home team advantage does come into play when it comes to predicting how teams will fare in the tournament based on their regular season data, it doesn't so much come into play when it comes to the actual tournament. We'll look at the teams and their wins and losses for the 2019 season. So this is more or less how the seeding is compiled. There's also some strength of schedule that's included as well. So you can see Louisville is a number 1 seed, whereas Connecticut was actually a number 2 seed, despite the fact that Connecticut was undefeated and Louisville lost 2 games. But, like I said, strength of schedule and then playing more games also has an impact. Baylor was a number 1 seed. They lost a game. It's not uncommon. It's pretty rare that you see teams go undefeated. That being said, UConn women's team has a history of going undefeated. Like I said at the top of this presentation, they hold the record for most consecutive wins with 111, including 2 national championships. So they're typically a very strong team, and this is just kind of looking. Notre Dame was also a number 1 seed, so again, this strength of schedule comes into play here. There are some more teams as we go down here and look that we're going to see come up again when it comes time for the actual bracket. Was advanced statistics. Like I said, a lot of the models that I saw being built didn't really go into advanced statistics. They just kind of took what data was given and just basically made their model based on that. However, I wanted to go a little bit deeper into that because I felt like it might give me some sort of edge, and I'll discuss that a little bit more when it comes time for that actual model. But offensive rating, defensive rating, net rating, true shooting percentage, effective field goal percentage, especially effective field goal percentage. This is kind of a big deal now in modern basketball as the three-pointer is becoming more and more prevalent. More teams are taking them, and more teams are employing shooters that are better at effectively converting them, so to speak, making three-pointers. So effective field goal percentage is pretty important. Net rating is also very important, and I'm going to get into this a little bit here. So you can see some of these ratings. The blue is a winning team, and the yellow is the losing team. So you can see that typically the blue team has a higher offensive rating, which is a good thing, and a lower defensive rating, which is a little bit surprising, but perhaps not. Their net rating, the blue team, or the winning team, obviously much higher. Typically, the winning team has more assists. They have more baskets, so it makes sense. Turnover is pretty consistent. It's fairly low. You know, these teams are at the top of their game. They're not making a lot of mistakes, so to speak. Typically, the better shooting team is going to win. Like I said, the better shooting team is going to win. This also includes the three-pointers, like I talked about, and then free throws. I mean, they call them free. You don't want to leave those points on the table. So, offensive rating and wins for the seasons 2010 through 2019. These yellow points are the teams that would eventually go on to be the national champion. And so you can see pretty consistently here that the higher the team ranks in offensive rating throughout the league, the more likely they are to be national champion. So we would expect our national champion would probably be one of these teams. There are some instances where that wasn't quite the case, but for the most part you can see they're typically the most efficient teams. They don't leave points out there. And now we're going to do the same thing and look at defensive rating. So you can see typically the better defensive teams are also national champions. I don't think it comes as any surprise that teams that are good offensively and defensively have more success than teams that are good at just one or not good at either. So again, we would expect probably our national champion to be one of these, and we would assume that this would be the same or similar grouping to the offensive rating. I want to look at net rating and wins. This is basically the metric that combines defensive and offensive rating, and you can see the national champion, with some exception, is typically one of, if not the clear best team in the league. So there's no predictor for 2019 because that is the goal of this particular competition, is to predict who's going to win, although we do know, and I could have included it, but I decided not to for the sake of making this a little more transparent here. So you can see these are all our national champions. You know, they're usually leaving the field behind, although there are some years where there's more grouping, more tight grouping, and that's likely due to just stronger competition. So now let's get into the approaches. For the men's tournament, I used 4 different kind of logistic regression models, basically, in order to 3, I guess I should say, and then a final model, which was a combination of the first 3. But so it started with seed-based logistic regression, basically just converting historic seeding into seed differential and predict winners using logistic regression. It was a really simple, straightforward approach. Surprisingly effective. Like I said, typically the higher ranked teams do better, which is not surprising. However, this model can be improved on, and we'll see that come into play. Average rank-based logistic regression using provided Massey ordinals. These are expert rankings, create composite scores based on the final day of the season. So right before the tournament, use those Massey ordinals, those rankings, and then you predict those winners based on logistic regression for the team's composite scores. The 538 ELO logistic regression was something that actually I found was very interesting. 538 is a Kaggle user who was the first person to implement ELO into this NCAA tournament prediction competition. However, ELO is a zero-sum based calculation that accounts for home court advantage, margin of victory. It utilizes a K factor which gives relatively high weight to recent performance, and it also rolls over from year to year, meaning that the larger data set you have, the more accurate your ELO is going to be, as the more consistently successful teams will continue on their path of success, and the less successful teams will continue to be less successful. And then the final model is going to be a combination of mean select ranking score and normalized ELO rating. So it's going to be a combination of something along the lines of this average ranked based, but it's going to be a little bit more specific, and then these normalized ELO, and I'll get into that as we get there. And then for the women's tournament, started with the same thing, seed-based logistic regression, basically just a baseline to see how the seeding would play out. Again, converting historic seeding into seed differential and predict winners using logistic regression. There's less data for the women than there is for the men. Again, the men goes back to 1985, women's only goes back to 1998. However, this is still a surprisingly accurate predictive model. And then the model that I used to build my bracket was an XGBoost model, a boosted random forest, utilizing a Cauchy objective function to train the model on mean absolute error. And I'll discuss this when we get there. This tournament with seed-based logistic regression. Again, our baseline, basically just merge our data frames into one usable set, and we have the seeds, the winning seed, the losing seed based on the team IDs, and then the seed differential, and then this is what we're going to actually use to perform our regression on. The seed differentials with knowledge of the results, create an X and Y training data sets, and perform logistic regression. And you can see that the lower or higher ranked teams have more success based on seed differential here. The higher the seed, the more likely the team is to emerge victorious. So fitting our model based on our seed differentials, we end up with a log loss of about 0.55, which again is not great, but it is a pretty good starting point. We're going to improve on this a little bit as we go. So moving on to average rank-based regression. Again, this is utilizing the Massey ordinals provided on Kaggle, creating a composite score based on final day rankings, so the day right before the tournament starts. So the highest score possible for that team on that particular season leading into the tournament. This is something that I was talking about. Teams on a hot streak, on a winning streak, tend to do better, so that's something that we want to try to capture in our rankings, in our composite scores. So we're going to check for correlation between ranking difference and score difference. And this is kind of a plot here. You have your score difference and your rank difference. And then again, we want to create X and Y training sets and then perform a logistic regression. So here we are, we have our model right here, and let's see, did we improve? Well, we performed about exactly the same. So our final day rankings apparently aren't much better than just our baseline. However, this is a step in the right direction as we're starting to look at more data than just the simple what's provided to us. The 538, again, he's a Kaggle user, ELO logistic regression. And so I'm going to start by explaining ELO here. 1500 is considered the average ELO score, so every team starts there. It's a zero sum, meaning that in head-to-head matchup, the winner will accumulate points and the loser will lose points equal to the number gained by the victor. Home court advantage is a key part of ELO scores. Generally speaking, team is favored. That accounts for about 100 ELO rating points. Again, the baseline is 15. It's considered the average. 1300 is considered a bad team. 1700 is considered a great team. Anything outside of that, you're getting into terrible teams and historically great teams. So this is useful for regular season predictions. However, there are far fewer home games in the actual NCAA tournament. Like I said, many of them are played on neutral sites. So this is good for calculating based on the regular season data, but isn't necessarily going to come into play so much when it comes to the tournament. But it will help us decide our ELO ratings for each team leading into the tournament, which is going to come into the composite score at the end. ELO accounts for margin of victory and a balance between rating systems that do not. Teams gain or lose more ELO points with larger margins of victory, meaning the powerhouse teams are especially favored. So you see a lot of times the really good teams are just crushing their really bad teams. So in a 1 versus 16 matchup, sometimes a team will win by 30 points. That'll give them a huge amount of ELO points, increasing their score and decreasing the other team's score. This factors into the NCAA tournament, especially in the women's teams, because they're a little more top-heavy than the men. Again, both men's and women's, there are particular powerhouses that are usually very good. It's just more so in the women that's the case. But a real simple explanation is basically a multiplier is assigned to each game based on the margin of victory. And that can be seen in the coding, and I'll link to the coding so you can look at my whole Jupyter Notebook and my R code. That'll be in the description of the YouTube video. Year-to-year carryover is also a factor in teams' ELO score. Portion of the score is carried over from one season to next, which means that historically successful teams are consistently ranked higher, which is why you're going to see teams like UConn and Tennessee for the women versus, say, Duke and UNC, Kentucky, Kansas. In the men's team, they're going to be having higher ELO scores. And now this K factor is something interesting for ELO scores. It determines how quickly the rating reacts to new game results, so to efficiently account for new data but not to react too strongly to it. So the goal is to minimize autocorrelation. Too high a K rating fluctuates too much, too low, and ELO will take longer to recognize important changes. The optimal K for basketball is said to be 20, which implies that the high weight ought to be given to a team's recent performance. So this is going to be great for us, as we're looking to try to predict teams that are on a hot streak as they're going into the tournament. Like I've said plenty of times here, this is going to be something that's going to be key. The optimal is 20. I've seen people play around with things between, say, like 18 and 22, but for the most part, people stick to about 20. Basketball is subject to relatively little randomness. Game-by-game results are pretty noise-free, meaning that when a team is winning consecutive games, it isn't due to luck. They're just a good team, and their ELO rating should reflect that. So here we have the ELOs for the team. Again, I'll link my code in the description so you can take a look at how I got here, but this is basically just, we have one team over the years, and you can see the fluctuation in their score. And again, every year it's carryover. So a portion of this would have been carried over to the next year, which means that they had a really good 2014 season and then a really bad 2015 season to drop this much. But then they were able to pick it up and pick it up and pick it up and try to get back to where they were over here. Actual logistic regression based on the ELO scores, it's pretty similar to the seed rankings. We have our winning team ELO and our losing team ELO, and then our ELO difference, and we're going to perform logistic regression based on that. So we have our ELO difference. Again, a 1 means that team A won, and a 0 means that team A lost. So you can see here that despite the fact that the winning team had a lower ELO score, they actually ended up winning. And this is going to come into play in our logistic regression here. And we see a slight improvement. Again, not huge, but it is a bit of an improvement over our first two approaches, our base model and our final day rankings. So now we move on to the final model. This utilizes the full set of Massey ordinals. The Massey ordinals has something like 20 expert rankings of all the teams in the nation, basically. So what I did was I took the full set, I iterated through each set of expert rankings, calculated a log loss for each using just that particular expert's rankings to get a log loss for each expert. And then I took the top 4 and then I averaged them to move on with. So the highest performing metrics were Sagarin, Whitlock, Moore, and Pomeroy. You can see their log loss. Not as good as our final day rankings, our ELO ratings, or even just our base model. However, these are the 4 that we're going to move forward with. So create a composites model based on the standardized ELO ratings and top Massey rankings, then take the mean for logistic regression. So we can see we have their seasoned ELO and then their mean rank, and the seasoned ELO comes from just the ELO score, and then their mean rank comes from these expert rankings here. So we're going to combine the two basically and perform logistic regression to try to improve on our previous results. So we have our training results here based on these, about what we expected, maybe a little bit better. And then our test results, actually a decent improvement, not huge obviously, but considering we were seeing, you know, in the thousandths improvement, to see something in like this is decent. It's not terrible. So we can see the composite model is the superior model with the lowest log loss of any tested so far. And again, this is for the men's results. And then we would go on to use this model to predict the 2019 results. However, I did not, like I said, make a bracket for the men's results. I only did it for the women's. Seed-based logistic regression, again, this is just the baseline model, and there's obviously a bunch of code here. I did a ton of advanced statistics, EDA, to try to parse all that data out in R, and I'll link to the code so that you can take a look at all of it if you want and try to run it for yourself. But this works just the same way as it did before. I just did this in R versus in Jupyter Notebook, but basically convert the seeds to simple integers and calculate seed differential, create a prediction such that 1 means a win and 0 means a loss. You can see here we're just doing that. And then we want to fit a model and estimate prediction. Generalized linear model. For the stats package, you just take our model, our prediction based on our seed difference. Our data is our predictions, and then our log loss. So our log loss here for the women's is actually even lower than it was for the men's. However, like I said, there's maybe a little bit less parity in the women's tournament than there is in the men's. It's kind of top heavy, so you would expect this to sort of be the case. This score would have been good enough for 329th place. So it's a start. Like I said, I did not do log loss for my XG boost. I just built the bracket based on it. But this is kind of where I started, and then I wanted to improve on that by using my advanced stats and advanced metrics. Yeah, seed differential, we end up with inclusion similar to men's. The higher seed certainly has the advantage over a lower seed team. So this is almost exactly the same as what we saw with the men's. You know, we have sort of this line here where it indicates that the higher the team seed, the more likely they are to win, basically, which is unsurprising. For the bracket building, there's quite a bit of code for this section, so I'll mostly be focusing on the Cauchy function, XGBoost parameters, and the actual cross-validation. Again, I will link to all of my code so you can take a look at all of it. I'm just focusing on sort of the most important parts here. So when it comes to minimizing for MAE, right, this is what we want our eval metric and XGBoost to be. We want to use this Cauchy objective function. Penalizes errors equally, and the function y equals the absolute value of x is non-differentiable at x equals 0. So when you configure your XGBoost here to use eval metric MAE, the algorithm would still descend by MSE, which poses a problem if you're optimizing for MAE, which is what the goal of this was to actually do. So to avoid over-penalizing values further away from the mean, you compress the range of values of your target variable, such as normalizing, scaling, or log transform, but this still doesn't quite solve the problem. The function allows me to create a first gradient and a second Hessian derivative with respect to the prediction at a given training round. For this particular problem, the XGBoost was optimizing for predict points differential in order to train the tree model. So we have our gradient and our Hessian, and we're just trying to optimize these based on our predictions and our labels. In here, our labels is the points differential. So basically, we want to try to optimize our predictions to accurately predict the score outcomes of games. So, you know, we just kind of have something down here to try to optimize just some values. This is just a general function here that can be thrown into your XGB parameters so that we're actually training for MAE, not inadvertently training for MSE. I opted for reducing the learning rate, the ETA, I believe it's called, or my XGBoost from the default. This might lead to some overfitting on my end, but in order to curb this overfitting, I utilized subsamples at 35%, meaning I randomly took 35% of the training data prior to growing my trees. I also took a 70% subsample of the columns while constructing each tree. In order to make this model a little more expansive, I constructed 10 parallel trees during each iteration of boosted random forest. My second Hessian derivative minimum was set to 40, meaning that the leaf node sum of instance weight needed to be greater than 40 in order to continue partitioning. So our minimum child weight here, this would be our Hessian. It has to be greater than 40 in order to continue going, basically. So that's what we're trying to do here. This is our objective function, is trying to grow our tree in such a way that we're only taking the most important values, the most likely and important values. That's basically all we're doing. I increased the gamma, leading to a more conservative algorithm, minimum loss reduction required to make a further partition on a leaf node, and I kept my max depth relatively small in order to reduce overfitting that was likely to occur from my reduced ETA here. So I didn't make enormous trees. I just tried to do them or create them in such a way that I would kind of balance out the overfitting that I expected. And this is sort of a conservative model, and we'll see that when it comes time to actually talk about the bracket that it made. But that was the goal. Validating the model 10 times on 5 folds, but decided to keep my number of rounds small as I was under a bit of a time constraint wrapping this up, and it was just taking forever to iterate. This is something that, as I go forward, if I compete in this competition again, which I likely will, this took a lot of effort, and I have a pretty decent grasp of it and a good starter kernel to work off of. But this would be something that I would definitely want to increase going forward. It was just taking forever to iterate. Even with it set at 30 with 10 cross validations, this was taking me maybe 15 minutes to run, which is not too terrible considering iterating through the men's data for the ELO rankings. Every time I did that, which unfortunately I had to do multiple times because, you know, debugging code never goes smoothly. Every time I would do that, it would take over an hour for it to run. So I would just get up and leave my computer. So this is something that I wish I could have increased, but I just lacked the time and computing power necessary to really train this model well, or as well as I would have liked to. Just to be safe, I coded any of my predictions in my 2.5% margin of error and chose to code my predictions such that, I'm sorry, I also coded any predictions in my 2.5% margin of error, top and bottom, to be either the 2.5% or 97.5%. So there's nothing lower or higher there. We can see that down here. This is what I mean by that. So my predictions, this is just trying to be safe. And then this is something that I would probably try to tweak this based on my results, but I was trying to remain conservative and not have anything go too horribly wrong in my model. So anytime a 16, 15, 14, or 13 faced 1, 2, 3, or 4 seed, I always gave the favor to the the superior team, and then this is just saying the same thing here. Anytime 1, 2, 3, 4 faced 16, 15, or 14, they were guaranteed a victory regardless of what the model thought. So this is something that maybe I'd like to tweak as well. This kind of nixes the idealism of a Cinderella story, but is probably a safe bet most years. All things considered, my model performed pretty well. It accurately predicted the national champion. Here's the bracket that came out. Baylor was in fact the national champion, so I successfully predicted the national champion. I successfully predicted the runner-up Notre Dame. It successfully predicted 54 out of 63 games for an accuracy of 86%. So for a conservative model like I had, not too terrible. It did, however, give too much preference to higher seeded teams. It didn't allow for Cinderella teams. One such story was Missouri State, an 11 seed, made it to the Sweet 16, taking down a 6 and a 3 seed before finally falling to the 2nd seeded Stanford. This is something that my model just couldn't handle. It couldn't handle an 11 seed making it that far. So that's something that in the future I'd like to try to improve on. Overall, my model may have been too conservative, like I said. I did try to stick to the more conservative side, as I didn't want any major hiccups to come. My model had all 4 number 1 seeds making the Final Four, so maybe a little too much preference was given to higher seeds, as number 2 seeds Oregon and UConn took down number 1 seeds Mississippi State and Louisville in order to make the Final Four in reality. That being said, there's probably some sort of way to get combination of historical performance in there, as obviously UConn is one of the most successful women's basketball programs in history, so that would be something to look to, just sheer experience factor basically. But some things to tweak before the 2020 tournament, like I said, let the XG boost run for more than 30 rounds. I saw a lot of people were doing, 3,000 rounds, 5,000 rounds, whatever the case may be, but I just didn't have the patience or the computing power to really make that happen. 30 rounds was pretty good, 86% accuracy. However, I would like to up this number significantly. Give less preference to higher seeded teams. Again, this is it's one of those things, it's a pretty safe bet that a 1's going to beat a 16, or a 2 is going to beat a 15. That being said, as you get further and further towards the national championship, maybe you have, like Missouri State, this an 11 seed is going to take down a 6 and a 3 seed, and just looking for ways to sort of factor that into my model, and then experiment with different stats to apply in the XG boost. So I use my advanced statistics, which I showcased up at the beginning of this. That being said, I feel like net rating on its own could possibly have been as effective as all of the parameters that I included. I didn't get a chance to play around with this, as I spent a lot of time really just building the model and getting it to work right, quite frankly. That being said, I think that there's some parameter selection that I could do that would maybe even improve on this model, maybe get it around 90%. I don't expect my model to accurately predict the whole tournament, but certainly strive towards that. If you've made it this far, thanks for listening. There was a lot to get through. I left a lot out. Like I said, I'll link all of my codes in the description. I look forward to competing in 2020 for real, rather than just as a challenge or an exercise. This was a fun but tough project, and I recommend anyone give it a shot if you're interested in basketball or machine learning.